In this lecture, we deal with the classification of linear systems. We wish to study the general case of an arbitrary 2 by 2 matrix and classify the possible phase portraits that can occur. A two-dimensional linear system is x dot is equal to ax plus by, y dot is equal to cx plus dy, where a, b, c, d are parameters. So written compactly in vector form, we get x dot is equal to a times x, where a is a, b, c, d and x is x and y. Note that we will be using green to denote vectors. So we seek trajectories of the form x of t is equal to e to the lambda t times v, where v is not equal to 0, is some fixed vector to be determined, and lambda is a growth rate which is also to be determined. To find conditions on v and lambda, we substitute x of t is equal to e to the lambda t times v into x dot is equal to a times x to obtain lambda e to the lambda t times v is equal to e to the lambda t a times v. So cancelling e to the lambda t gives a times v is equal to lambda times v. So the solutions exist if v is an eigenvector of a with corresponding eigenvalue lambda. So the solution x of t is equal to e to the lambda t times v is an eigen solution. The eigenvalues of a matrix A are given by the characteristic equation, the determinant of A minus lambda I is equal to 0, where I is the identity matrix. So for a 2 by 2 matrix A with entries A, B, C and D, the associated characteristic equation becomes the determinant of A minus lambda, B, C and D minus lambda is equal to 0. Expanding the determinant yields lambda squared minus tau lambda plus delta is equal to 0, where tau is the trace of A, which is equal to A plus D, and delta is the determinant of A, which is equal to AD minus BC. Then lambda 1 is equal to tau plus tau squared minus 4 delta square root divided by 2, and lambda 2 is tau minus tau squared minus 4 delta square root divided by 2. Then lambda 1 and lambda 2 are the solutions of lambda square minus tau lambda plus delta is equal to 0. Note that the eigenvalues depend only on the trace and the determinant of A. Normally, the eigenvalues are distinct, so lambda 1 is not equal to lambda 2, In this case, the corresponding eigenvectors v1 and v2 are linearly independent and span the entire plane. In fact, any initial condition x0 can be written as a linear combination of eigenvectors. For example, x of naught is equal to c1 v1 plus c2 v2. So the general solution is x of t is equal to c1 e to the lambda 1t times v1 plus c2 e to the lambda 2t times v2. So let's consider an example. Solve the initial value problem. X dot is equal to x plus y and y dot is equal to 4x minus 2y. Subject to the initial conditions, x dot y dot is equal to 2 minus 3. So writing in matrix form, we get x dot y dot is equal to 1 1 4 minus 2 times xy. So we first find the eigenvalues of the matrix A. So for the matrix, the trace of A is equal to minus 1 and the determinant of A is equal to minus 6. The characteristic equation is lambda squared plus lambda minus 6 is equal to 0, which gives lambda 1 is equal to 2, lambda 2 is equal to minus 3 as solutions. Now we need to find the eigenvectors. So given an eigenvalue lambda, the corresponding eigenvector v, which is composed of v1 and v2, satisfies 1 minus lambda 1, 4 minus 2 minus lambda times v1 v2 is equal to 0 0. So for lambda 1 is equal to 2, we get minus 1 1 4 minus 4 times v1 v2 is equal to 0, which gives v1 v2 is equal to 1 1, or in fact any scalar multiple thereof. For lambda 2 is equal to minus 3, we get 4 1 4 1 times v1 v2 is equal to 0, which gives us v1 v2 is equal to 1 minus 4. In summary, v1 is equal to 1 and 1 and v2 is equal to 1 minus 4. So we can write the general solution as a linear combination of the eigen solutions. The general solution is x of t is equal to c1 times 1 1 e to the 2t plus c2 times 1 minus 4 e to the minus 3t. We now also need to compute c1 and c2 to satisfy the initial condition x naught y naught is equal to 2 minus 3. At t is equal to 0, the general solution becomes 2 minus 3 is equal to c1 times 1 1 plus c2 times 1 minus 4, which ends up giving 2 is equal to c1 plus c2 and minus 3 is equal to c1 minus 4c2, which yields c1 is 1 and c2 is 1. So finally we have the solution to the original initial value problem, which is x of t is equal to e to the 2t plus e to the minus 3t, and y of t is equal to e to the 2t minus 4e to the minus 3t. Now let's draw the phase portrait for the system. The system has two eigenvalues, 2 and minus 3. So we have one positive and one negative eigenvalue. The first eigensolution grows exponentially, and the second eigensolution actually decays. So this implies that the origin is a saddle point. The stable manifold is the line spanned by the eigenvector V2 is equal to 1 minus 4, and the unstable manifold is the line spanned by the eigenvector V1 is equal to 1, 1. With saddle points, a typical trajectory approaches the unstable manifold as t tends to infinity, and the stable manifold as t tends to minus infinity. So now, armed with all of this information, let's draw the phase portrait. So we plot y versus x. We first highlight the stable eigendirection, and then highlight the unstable eigendirection. And we now go ahead and complete the phase portrait. And that's the completed phase portrait. Now let's sketch the typical phase portrait for the case lambda 2 less than lambda 1 is less than 0. As lambda 2 is less than 0 and lambda 1 is less than 0, the eigensolutions decay exponentially, and the fixed point is a stable node. The trajectories would approach the origin tangent to the slow eigendirection, which is defined as the direction spanned by the eigenvector with the smaller absolute value of lambda. Note that as t tends to minus infinity, that is going backwards in time, the trajectories become parallel to the fast eigendirection. So now let's plot the typical phase portrait. So we plot y versus x. We highlight the slow eigendirection. Then we highlight the faster eigendirection. That's the stable node. That's where it would be fast, and that's where you'd be slow. And now we go ahead and complete the phase portrait. Now, what happens in the case if the eigenvalues are complex numbers? In this case, the fixed point is either a center or a spiral. Now let's go ahead and plot a center. So that's what typical centers would look like. Now we plot a spiral. Essentially, the trajectories spiral inwards. Note that in the center, the origin is surrounded by a family of closed orbits. The centers are neutrally stable as nearby trajectories are neither attracted nor repelled from the fixed point. Now let's look at the eigenvalues in some detail. So lambda 1 2 is equal to 1/2 trace plus minus trace square minus 4 delta square root. So we get complex eigenvalues when trace square minus 4 delta is less than 0. So let's write the eigenvalues as lambda 1 2 is equal to alpha plus minus I omega, where alpha is equal to trace by 2 and omega is 1/2 of the square root of 4 delta minus trace square. Now omega is not equal to 0, so the eigenvalues are distinct, and the general solution is x of t is equal to c1 e to the lambda 1 t times v1 plus c2 e to the lambda 2 t times v2. Now note that the lambdas are complex, and so the c's and the v's are also complex. Now what this essentially means is that x of t involves linear combinations of e to the alpha plus I omega times t. By Euler's formula, e to the I omega t is cos omega t plus I sin omega t. So x of t is a combination of terms involving e to the alpha t cos omega t and e to the alpha t sin omega t. Hence we have exponentially decaying solutions if alpha, which is the real part of lambda, is less than 0, and growing solutions if alpha is greater than 0. So the fixed points are stable spirals if alpha is less than 0 and unstable spirals if alpha is greater than 0. If alpha is equal to 0, i.e. we have pure imaginary eigenvalues, then the solutions are periodic with period capital T is equal to 2 pi by omega. The oscillations have fixed amplitude, and the fixed point is a center. Now what happens as the eigenvalues are equal? So far we have been assuming that the eigenvalues are distinct. So let's assume that lambda 1 is equal to lambda 2 is equal to lambda, and consider two cases. Case 1, there are two independent eigenvectors corresponding to lambda. Or case 2, there is only one. So now let's consider case 1 in some detail. In this case, the eigenvectors span the plane and every vector is an eigenvector with the same eigenvalue lambda. So let's get a better understanding of this. Write an arbitrary vector x naught as a linear combination of the two eigenvectors. So x naught is equal to c1 v1 plus c2 v2. Then a times x naught is equal to a times c1 v1 plus c2 v2 is equal to c1 lambda v1 plus c2 lambda v2 is equal to lambda times x naught. And so x naught is an eigenvector with eigenvalue lambda. Then if lambda is not equal to 0, all trajectories are straight lines through the origin. X of t is equal to e to the lambda t times x naught, and the fixed point is a star node. If lambda is equal to 0, the whole plane is simply filled with fixed points. The system is x dot is equal to 0. For lambda not equal to 0, we get the following phase portrait, where we essentially have straight lines that are flowing through the origin and the point is a star node. And now let us consider case 2. The eigenspace corresponding to lambda is one-dimensional. So for example, any matrix of the form A is equal to lambda B 0 lambda with B not equal to 0 has only a one-dimensional eigenspace. In fact, we request that you show this is true as an exercise. When we have only one eigendirection, the fixed point is a degenerate node. So now let's plot the typical phase portrait. So that's the only eigendirection. And that completes the typical phase portrait. So as t tends to positive infinity and t tends to negative infinity, all the trajectories become parallel to the one eigendirection. One can now show the type and stability of all the different fixed points on a single diagram. So we plot the trace versus the determinant delta, and we also plot the curve t square minus 4 delta is equal to 0. So that's where the saddle points live, that's where the unstable nodes are, that's the region for unstable spirals, centers, stable spirals, stable nodes, and along the curve you will have stars and degenerate nodes. And finally, that's the point for non-isolated fixed points. So now we plot simple caricatures for the typical phase portraits. So you have the unstable spiral, a center, stable spiral, stable nodes, stars, and finally degenerate nodes. So we are finally done. It was hard work, and I think we deserve a smiley face at the end of it all. The intention of this lecture was to look at a classification of two-dimensional linear systems in terms of the qualitatively different phase portraits that could come from such systems. So when you're looking at a two-dimensional system, you have equations of the form x dot is equal to ax plus by and y dot is equal to cx plus dy, where a, b, c and d are parameters. And then you could ask questions of the form, what happens when you have negative eigenvalues but they are distinct? What happens when you have complex eigenvalues? What happens when the eigenvalues are in fact the same? So essentially what we did in this lecture was we systematically went through all the numerous cases and then eventually put it all together in a plot where you plotted the trace versus the determinant, highlighting the qualitatively different phase portraits that could occur depending on where you were in the trace versus determinant plot.